how do you find that point? Well, one way to find the point is to use an algorithm. And so where is the minimum in beta 1? The simplest solution is that's a grid search problem. And you'll see that in algorithms, someone will say, well, we used a grid search. Anybody can do a grid search, especially when we only got one beta. A grid search just means try all the betas. You can't try all of them because there's an infinite number. But try a whole bunch of them. This is a grid search algorithm. Try lots of beta 1s and pick the best. So we let beta 1 start at 0 and increase by 0.001. And so we had to evaluate the function a bazillion times, but who cares? The computer's good at that. And out comes this yields beta 1, what do we put it? Star. But that beta 1 is not necessarily the right answer. Because where this one's kind of obvious, but that beta 1 could be in the wrong place completely, or it could only be accurate to 0.001. Most of the time we don't care. And we go, oh, we'll just do a grid search and we'll get close to the right answer, which is lovely. Except in multivariate problems, life doesn't work like this. Because a grid search, suppose we had to search in 2 dimensions. We're trying to, I don't know if I can draw it. We're trying to minimize the 3-dimensional function that looks like this. And the actual answer is this one, and sometimes we get stuck over there and we have a derivative problem up there. And we can do a 2-dimensional grid search. Well, in here, maybe I had to check 10,000 possible betas. And 10,000 possible betas, your phone can run that easily. And the computer, even the crappy computer on your desk can run that super easy. So 10,000 is 10 to the 4th power. If you have 2 dimensions, that's 10 to the 8th power, which is 10 million times. My computer can do that. Your computer maybe not. But that's only 2 dimensions. But all the problems we work in have lots of dimensions. So we have, in general, 10 to the 4 times p betas for the grid search. No computer in the world can solve that for even p equals 3. And So just the simple uh, tobacco data. Tobacco data has something like 27 elements in it. That would be 10 to the 27 times 4, which is 10 to the 100th, which is more than all the atoms in the universe, or whatever the expression you want to use. The computers can't do that. It cannot be done. And so a grid search is a simple algorithm that solves problems that calculus can't solve, but a grid search can't solve most of the problems that we care about in multivariate statistics. It can be the basis of algorithms, and there are problems that are solved by grid search all the time, but typically not the ones in multivariate statistics. So, and this is impossible. When I was younger, I thought, we'll just wait for the computer to get faster, and then we'll be able to solve this problem. Because computers get faster all the time. Every computer is faster than the old one, and life doesn't work that way. It does not happen. The problem is the size of the problem grows faster than the computational speed. You will always face problems that can't be solved by the computer, no matter how big your computer is, and it's just too big a problem. And then the computer comes back and says, no, I can't do that. You go, oh, I'll get a bigger computer. There is no computer that can solve the problems. So that means you need a different algorithm. And this is where the computer scientists and the statisticians intersect. The computer scientists have entire fields devoted to algorithms. And it's super cool. They are really good at algorithms. And they prove that their algorithm finds the right answer, mathematically prove. And so basically they've solved this problem by using computational tricks. The statisticians, on the other hand, have very specific kinds of functions. The computer scientists want this function here to have all sorts of complicated, a very general function. For any function, they try to prove that they can find the minimum of that function. A statistician will go, I'm not so interested in any function. I have a particular function that I want to minimize, like the sum of the squared errors, like least squares does. Well, that's a particular function. And I don't need a grid search, and I don't need an algorithm to do that because I've got an equation to do that. There's no equation for logistic regression. There's no formula for doing that. It relies on an algorithm, but fortunately, the algorithm is minimizing a smooth curve. And so the calculus gets to help, and it's really easy for the algorithm to converge to the right answer. I've never seen logistic regression converge to the wrong answer. I wouldn't know that it happened in the first place, because it's a very smooth, you're still minimizing a smooth function, you're still using calculus, it just doesn't have a formula that we can use. So, how does this relate to cluster analysis? Well, cluster analysis is solving k-means cluster analysis. So, I guess we go here. K-means cluster analysis. the game is to find the for you have to there's a reason it's called k-means. K is equal to 4. Why did I choose 4? Well, that's what happens for our. You have to specify what k is. You don't get to there's no magic way to know what it is. You just have to know what it is, or you try a bunch of different values, which becomes hard because k-means cluster analysis is hard, and I'll show you why it's hard. Find the 4 groups, clusters, in the data that minimize and what's called an objective function. Objective function. So and the different types of k-means cluster analysis, it gives you choices that the typical objective function in k-means is the summation. I don't know whether to call them x's or y's. There's no response variable, so I guess I'll call them x's. xi minus xi bar, in some sense quantity squared, and the